Our third simple case looks at a spiral of current carrying wire. This is known as a solenoid. It's shown below as a red spiral with a current flowing in it. And the solenoid creates a field that looks like a bar magnet or a dipole field, similar to that of a single loop of wire. The field lines are shown, and you can see that they have a dipole pattern, though they're a little bit stretched from the single loop. Again, there's a north and south pole, and again, it's symmetric around the axis of the solenoid. The magnetic field doesn't depend much on the position inside the solenoid. This can be seen by looking at the magnetic field lines inside the solenoid and seeing that they're nearly parallel. As a matter of fact, in the case where the solenoid is very long, then the field inside the solenoid does not depend on the parameters like the radius of the solenoid or the length of the solenoid. It depends simply on mu0, which is the permeability, times m, which is the number of turns per length, times the current. The direction of the magnetic field inside follows the right-hand rule as for the loop. So you curl your fingers in the direction of the current and your thumb points in the direction of the B field. For a current of 1 amp, what is the magnitude of the B field for different values of the number of turns per length? For 10 turns per meter, the magnetic field is 1.3 times 10 to the minus 5 Tesla. If you increase the number of turns by a factor of 10 to 100 turns per meter, the magnetic field goes up by a factor of 10 to 1.3 times 10 to the minus 4 Tesla, which is about the strength of the Earth's magnetic field. If we increase the number of turns by a factor of 100 to 10,000 turns per meter, we're now getting to a value that's similar to a bar magnet, or 1.3 times 10 to the minus 2 Tesla.